Welcome to EFSA's E-learning on uncertainty analysis for chemical risk assessments. I'm Andy Hart and this is the last of 3 presentations in the course. The course focuses on practical options for applying EFSA's guidance on uncertainty analysis in chemical risk assessments, and the key principle throughout is to tailor the uncertainty analysis to what is necessary and useful for each assessment. In presentation 1, I introduce some key concepts which EFSA's uncertainty guidance uses: standardized procedures and case-specific assessments, and standard and non-standard uncertainties. I described how to identify sources of uncertainty, and I explained that when using a standardized procedure, if no non-standard uncertainties are found, no further uncertainty analysis is required. In all other assessments, further analysis is needed to assess overall uncertainty, the combined impact of all identified uncertainties on the conclusion of the assessment. In the second presentation, I explained why the uncertainty guidance recommends assessing overall uncertainty quantitatively using probability, and I described in detail the basic option for doing this, which is to assess the combined impact of all the uncertainties together in a single step using expert judgment. I also explained that where EFSA is required to provide firm conclusions, you can do this using defined thresholds for the level of certainty that is required. In this presentation, we move on to refined options, where some sources of uncertainty are assessed separately before assessing overall uncertainty. These principles and methods are applicable to all types of chemicals, but to keep things simple, I will continue with the example I introduced in presentation 2, a contaminant. This example is based on the Contam Panel's 2011 opinion on T2 and HT2 toxins. In this example, the exposure estimates were well below the TDI, but the assessors identified a list of uncertainties affecting both exposure and hazard, so the true values could be either lower or higher. In the previous presentation, I described the basic option for assessing overall uncertainty, which is to assess the probability of exposure being below the TDI by expert judgment, considering all the uncertainties together, using EFSA's approximate probability scale. So, when is the basic option sufficient? If we imagine a hypothetical alternative situation where the exposure estimates are far below the TDI and all the uncertainties are small, then it should be easy to judge that your probability for exposure being below the TDI is very high, implying a high certainty of no concern. In this type of situation, the basic option is likely to be sufficient for advising risk managers. Similarly, if exposure and the TDI were reversed, with exposure being far above the TDI, it should be easy to judge that your probability for exposure being below the TDI is very low. Here again, the basic option is likely to be sufficient. So, when are refined options needed? This is more likely for cases like the T2 and HT2 toxins, where exposure and the TDI are close together and the uncertainties are larger. In this type of situation, assessing overall uncertainty in a single step, considering all the uncertainties simultaneously, may be more difficult, and it may be easier to start by quantifying some of the uncertainties separately before considering the overall uncertainty. Another reason why it might be difficult for the assessors to quantify all the uncertainties together is that some uncertainties affect the exposure estimate while others affect the hazard. And most assessors have expertise either on exposure or hazard, but not both. So a simple refined approach which may be helpful is to ask the exposure experts to quantify the exposure uncertainties and the toxicologists to quantify the hazard uncertainties, and then combine the two by calculation. I'm going to describe 2 ways of doing these 3 steps, starting with a simpler option, probability bounds, which may be sufficient in many cases. A probability bound is defined in EFSA's uncertainty guidance as a probability or approximate probability for a specified range of values. For example, suppose the exposure experts judge that there is at least 95% probability that the highest 95th percentile exposure is below 90 nanograms per kilogram body weight per day, considering all the populations they are assessing and taking into account all identified uncertainties affecting the exposure assessment. This is a probability bound for exposure. It's important to recognize that the two 95s here refer to different things. The 95th percentile exposure refers to the variability of exposure. It makes clear that the exposure assessment is focused on that percentile. The 95% probability, on the other hand, is quantifying uncertainty, not variability. It says the assessors are 95% certain that the actual 95th percentile exposure is below 90 nanograms per kilogram body weight per day. Suppose also that the toxicologists judge there is at least 95% probability that the TDI is above 100 nanograms per kilogram body weight per day, taking into account all identified uncertainties affecting the hazard assessment. This is a probability bound for hazard. We can assess uncertainty for the conclusion on risk by combining these two judgments using probability bounds analysis. This is defined in EFSA's guidance as a method for combining probability bounds for inputs in order to obtain a probability bound for the output of a deterministic model. In my example, the model could be the ratio of exposure to hazard. Combining the judgments above, there would be at least 90% probability that the ratio of the highest 95th percentile exposure to the TDI is less than or equal to 0.9. That's 90 divided by 100. The ratio is less than 1, so there is at least 90% probability that exposure is below the TDI, a useful result because it might be sufficient to conclude there is no health concern. How does this calculation work? How do we get from two 95% bounds for exposure in the TDI to a 90% bound for the ratio? A simple but informal way to think about this is in terms of lost probability. We judge there is at least 95% probability that the highest 95th percentile exposure is below 90 nanograms per kilogram body weight per day. So there is less than 5% probability that it is higher than 90 nanograms per kilogram body weight per day. In the language of lost probability, we have lost less than 5% probability to higher exposures. Similarly, we judge there is at least 95% probability that the TDI is above 100 nanograms per kilogram body weight per day. So we have also lost less than 5% probability to lower TDIs. Then we simply add the lost probabilities for higher exposures and lower TDIs to find the lost probability for higher ratios. In our example, we have lost less than 5% for exposure and less than 5% for the TDI, so in total we have lost less than 10% to higher ratios of exposure to the TDI. In other words, there is at least 90% probability that the ratio is less than or equal to 0.9. So, thinking in terms of lost probabilities requires only simple arithmetic. You simply add them up. It is not necessary to know or use the underlying theory that justifies this simple calculation, but if you are interested, you can find a more formal explanation and references in Annex B13 of EFSA's opinion on the principles and methods for uncertainty analysis. Before we look in more detail at the method, we need to consider a potential issue with terminology. The TDI is a type of health-based guidance value, so there might be concern that expressing uncertainty about the TDI will conflict with its official status and cause difficulties in communication with consumers and stakeholders. If so, we can refer instead to the uncertainty of the information on which the TDI is based. The TDI is derived by establishing a reference point, which might be a no observed adverse effect level or a benchmark dose, and dividing it by an appropriate uncertainty factor. So a possible solution is to express uncertainty for the reference point divided by an appropriate uncertainty factor, or RP over UF, rather than for the TDI itself. Other possibilities exist, but for the purpose of illustration, I will use RP over UF in the rest of this presentation. So far, I've given an example of a probability bounds calculation with one specific set of input values. The next slide provides a general step-by-step description of how you can apply probability bounds to any assessment where you are comparing exposure and hazard to assess risk. First, agree on a probability threshold for a firm conclusion that exposure is below the TDI. How much certainty is required? Subtract your probability threshold from 100% to set an upper bound for loss probability. Divide the loss probability into two parts, for exposure and hazard. Subtract the loss probability for exposure from 100% to set the probability required for a conservative upper bound estimate of exposure. Elicit the upper bound estimate of exposure from your exposure experts following the semi-formal elicitation process that are described in presentation 2. Set the probability required for a lower bound estimate of RP over UF by subtracting the loss probability for hazard from 100% and elicit the lower bound estimate of RPUF from toxicologists. Finally, divide the upper bound for exposure by the lower bound for RP over UF. If the ratio is less than 1, there is sufficient certainty for a firm conclusion that exposure is below the TDI. For example, suppose it was agreed that 90% probability of exposure being below the TDI is sufficient to conclude there is no health concern. This means that the upper bound for loss probability is 10%, and we might divide this equally, 5% for exposure and 5% for hazard. This means we need to elicit a 95% upper bound for exposure, and let's suppose the exposure experts judge this to be 90 nanograms per kilogram body weight per day. We also need a 95% lower bound for RP over UF, and let's suppose the toxicologists judge this to be 100 nanograms per kilogram body weight per day. This gives us a ratio of 0.9, which is less than 1, so we can conclude there is no health concern. If the ratio was a little above 1, it might be worth repeating the probability bounds analysis with a different split of the lost probability, giving more of it to the part of the assessment, exposure or hazard, which you think is more uncertain. If the ratio is much above 1, it will be more effective to move on to a more refined uncertainty analysis using probability distributions rather than repeating the probability bounds analysis. Before I go on to describe the more refined approach, let's look at the key difference between using probability bounds and distributions. For probability bounds analysis, I've described how listed probability bounds for exposure and RP over UF are combined by simple arithmetic to obtain a probability bound for the ratio. When using distributions, we elicit a probability distribution for the uncertainty of the exposure estimate and another probability distribution for the uncertainty of RP over UF, and we use Monte Carlo simulation to calculate a probability distribution for the uncertainty of the ratio between them. However, this is significantly more complicated, as we will see in the next slides, so it is worth trying the probability bounds approach first to see if it is sufficient for your assessment. A probability distribution quantifies the range and probability of possible values for a quantity of interest, in this case the highest 95th percentile exposure. The width of the distribution shows the range of values that are plausible, and the vertical axis shows the probability of different values within that range. The experts judged that the true value is most likely to be near the peak of the distribution, less likely to be in the tails, and has virtually no probability of being outside the distribution. Note that there is only one true value. The distribution represents uncertainty, not variability. The variability of exposure is addressed by focusing on the highest 95th percentile consumer. We generally use 5 judgments to elicit a full distribution: the lower and upper plausible bounds, then the median, and finally the lower and upper quartiles. The judgments are done in that order to reduce the risk of bias, and they divide the expert's plausible range into 4 equally probable parts. The basic minimal steps to elicit a distribution are similar to those I described for assessing overall uncertainty in presentation 2. The key difference is that we are working with distributions here, so the facilitator needs to fit an appropriate distribution to each expert's judgments and then also to the consensus judgments. Various tools for fitting distributions are available online, but eliciting and fitting distributions well requires specialist expertise, so it is advisable to seek support, which is available from EFSA's Cross-Cutting Working Group on Uncertainty or the Assessment Methodology Unit. Here is a hypothetical example of what a distribution for exposure might look like. It is very loosely based on the example for T2 and HT2 toxins which I used earlier. The upper end of the distribution is close to the highest estimate in the EFSA opinion, 91 nanograms per kilogram body weight per day, reflecting the idea that it is meant to be conservative, with most of the probability below that value. This is a normal distribution fitted to 5 values which I made up for the purpose of illustration. A lower limit of 25, an upper limit of 100, a median of 65, and quartiles of 55 and 75. In a real assessment, the values would be consensus judgments made carefully by the exposure experts, taking into account both the evidence and the list of uncertainties documented in the opinion. And here is a hypothetical example of what the distribution for RP over UF might look like. Again, it is very loosely based on the T2 and HT2 example. The lower end is close to the TDI determined by the panel, 100 nanograms per kilogram body weight per day, reflecting the idea that this is also meant to be conservative, with most of the probability above that value. In this example, my hypothetical values resulted in a beta distribution. In a real assessment, the values would again be consensus judgments made carefully by the toxicologists, taking into account both the evidence and the list of uncertainties documented in the opinion. If the experts cannot agree on a consensus distribution, this is of course part of the scientific uncertainty and needs to be taken into account. You can either report the range of opinion, for example by listing alternative distributions representing different views within the group, or if the range of opinion is very wide, you might report that the assessment is inconclusive. The next step is to combine the consensus distributions for exposure and RP over UF, and we do this by Monte Carlo simulation. This is a very simple application of Monte Carlo, which you can do in an Excel spreadsheet, though it is much better to use statistical software such as R, for which specialist support is available. The simulation uses the elicited distributions as inputs. It samples one value from the distribution for exposure and one value from the distribution for RP over UF and calculates the ratio of those values. It then repeats this process a large number of times and uses the resulting values to build a distribution for the ratio of exposure to RP over UF. The output distribution is not smooth because it is made up of a number of samples, in this case 10,000 samples. If I did more samples, the distribution would become smoother, and you need to do enough samples to get a stable estimate for the output of interest. In this case, what we are interested in is the probability that the ratio is less than 1. In other words, the probability that the highest 95th percentile exposure is less than RP over UF. We get this from the area under the distribution below 1 as a percentage of the total, in this case more than 99%, meaning there is more than 99% probability that the highest 95th percentile exposure is less than RP over UF. An important difference between using probability bounds and distributions is that probability bounds analysis is conservative. It will give you lower probabilities than using probability distributions and Monte Carlo. This is because probability bounds uses only the specified bounds and makes no assumptions about the width or shape of the uncertainty distributions, and also because it makes no assumptions about dependency between the uncertainties affecting exposure and hazard. whereas combining probability distributions using simple Monte Carlo requires distributions quantifying the expert's judgments about the full range of possible values and assumes the distributions for exposure and hazard are independent. This assumption of independence introduces an extra source of uncertainty, which must be taken into account when assessing overall uncertainty. This is because if there are dependencies, they might significantly increase or decrease the overall uncertainty. So the key thing is to check whether dependencies are present. These distributions quantify uncertainty, not variability, so we're not talking here about correlations between variables. The uncertainty distributions for two quantities are dependent if assessors think that learning more about one of them would alter their uncertainty about the other one. You can check this by asking your experts, if you discovered that the true highest exposure was here, would it change your distribution for RP over UF, and vice versa? If the experts think dependencies are present, you will need specialist support to help you assess their impact and take it into account. If you would like to see examples where this was done, look at EFSA's 2020 and 2021 reports on cumulative risk assessment for pesticides. Every refined uncertainty analysis must end with assessment of overall uncertainty by expert judgment. This is necessary because even when some uncertainties have been quantified and combined by calculation earlier in the assessment, you always need to take account of any additional uncertainties that have not yet been quantified, including any assumptions or dependencies affecting calculations used in the uncertainty analysis. You can do this by using expert judgment to adjust the probabilities that were calculated in earlier steps of the uncertainty analysis. The approximate probability scale is helpful for this. Identify which range your calculated probability is in, and consider what adjustment is needed, if any, to take account of the additional uncertainties and dependencies which are present. This should be done by semi-formal expert elicitation, following the same process I described in presentation 2. If the assessors consider that no additional uncertainties or dependencies are present, no adjustment is needed. Detailed advice on how to carry out adjustments of this kind is provided in section 16 of the uncertainty guidance. You can find examples where adjustments were made for additional uncertainties and dependencies in EFSA's reports on cumulative risk assessment for pesticides. How you report the results of the uncertainty analysis depends on what type of conclusions are required for the type of assessment you are doing. If firm conclusions are required, use defined probability thresholds, which I introduced in the previous presentation, to decide what conclusion is appropriate. For example, concern, no concern, or inconclusive. Otherwise, report the probability explicitly as part of the conclusion, rounded to avoid a misleading impression of precision. For further advice, see EFSA's guidance on communicating uncertainty in scientific assessments. When you put them together, the methods I've described in these 3 presentations provide a tiered approach to applying EFSA's uncertainty guidance in chemical risk assessments. The first presentation described the systematic identification of uncertainties and a very simple first tier for assessments using standardized procedures. The second presentation described Tier 2, and the third presentation described Tier 3 and Tier 4. I expect that Tier 1 or Tier 2 will be sufficient for many chemical assessments, and that few will need to go beyond Tier 4. I've not discussed uncertainty analysis for genotoxicity, but that can also be addressed using the methods in Tiers 1 to 4. I will show you the tiers again at the end of this presentation, but first I will talk very briefly about Tier 5, where a large range of more refined case-specific methods are available. These are useful for complex or highly uncertain assessments where the judgments required in Tier 4 are difficult, and they work by assessing some exposure or hazard uncertainties separately in more detail before combining them with the other uncertainties. Here are some examples of more refined options from published EFSA assessments. The details of these methods are too complex to cover in this e-learning, and anyway, you will need specialist support if you want to consider them for your assessments, so the specialist can guide you through the details. There is also a WHO IPCS guidance document which introduces a probabilistic approach for hazard characterization, although this would be a major change from current methods and would need review and further development to implement within EFSA. I've mentioned several times the importance of tailoring the uncertainty analysis to the needs of the assessment, and the purpose of the tiered approach is to help with that. Of course, this requires planning. Uncertainty analysis is an integral part of the risk assessment, not an add-on at the end. So you need to plan the uncertainty analysis at the same time as the rest of the assessment, applying EFSA's framework for protocol development if this is appropriate for your area of work. Decide whether basic or refined options are appropriate, request specialist support if needed, and include time for uncertainty analysis in your work plan and meetings. Be prepared to revise your plan if additional uncertainties emerge or more refined methods are needed. Before we close, it's important to make you aware of the need for calibration of standardized procedures, as these are used in most regulatory assessments. Calibration is defined in EFSA's uncertainty guidance as the process of evaluating whether a standardized procedure is appropriately conservative, and if necessary, adjusting it to achieve this. And it should be done every time you review a standardized procedure or develop a new one. Methods for this are described in section 6 of the uncertainty guidance. You can find an example of the first step of this process in EFSA's guidance on risk assessment for smoke flavourings. No example is yet available for the second step, but support is available from the working group on uncertainty. Uncertainty analysis does involve some extra work and will take more time, at least when you first start doing it. However, these costs are well justified by the benefits, which are substantial. For assessors, more thorough identification of the relevant uncertainties and a clearer shared understanding of their impact on the assessment, which will enable a better discussion and more confidence in the assessment conclusion. For risk managers, clearer understanding of how certain the assessors are of the conclusion, and therefore a better basis for decision making. When uncertainty analysis becomes familiar and integrated in your assessment procedures, it may actually save time that would otherwise be spent on less structured discussion of difficult uncertainties. In summary, these three presentations have introduced a tiered approach to applying EFSA's uncertainty guidance in chemical risk assessments. In all assessments, you need to systematically identify sources of uncertainty that are present. In Tier 1, when using a standardized procedure, if there are no non-standard uncertainties, it is sufficient to report that none were found. In Tier 2, assess all uncertainties collectively in a single probability judgment. In Tier 3, elicit probability bounds for exposure and hazard and combine to obtain a probability bound for the ratio. In Tier 4, elicit uncertainty distributions for exposure and hazard and combine to obtain an uncertainty distribution for the ratio. And in Tier 5, more refined case-specific methods where needed. The key principle is to tailor the uncertainty analysis to what is necessary and useful for each assessment. Specifically, use the simplest approach that seems likely to be sufficient and progress to more refined approaches only when needed. I hope this e-learning has provided you with a good starting point for exploring and applying these approaches in your work with EFSA, starting with the simpler options and seeking specialist support when you need it. To end, I'll leave you with some references to further information on some of the approaches we have covered. There is also the EFSA guidance document on communicating uncertainty. This is primarily aimed at communicators, but also contains useful advice for assessors to help you report the results of uncertainty in an effective way. Thank you very much for your attention.